Alright, so I'd intended on this being a relatively quick video. It didn't end up being so quick. I ended up having to do a lot of research for it, and because it's quite long, it's a pain in the arse to record. But anyway, let's have a look at RAS, RCD, and CAS timings, the dependencies inside them, and we'll have a general overview of DRAM read and write cycles in DDR3 and DDR4, and we'll finish with how to decide what RAS timing values to use. We're going to be quite technical on DRAM operation, so I should have some sources in the description to read and touch up on the topic. So let's start. In a DRAM array, we can select any address, any cell on the array by selecting its row and its column. So a row would be here and a column would be the vertical. And so that would arrive at this address. To select a row, we're going to assert the word line of that row. So asserting a word line, the word line actually connects all of the cells in that row. And what we're doing when we select when we assert the word line is we're actually powering on the access transistors in each of these cells. And so all of these cells, the charge that's in the capacitor in the cell will then get shared onto the bit line. And the bit line will then take that charge down to a sense amplifier. Because they're initially the bit lines are pre-charged to half of the operating voltage. So depending on whether there's a 1 or a 0 in the DRAM cell, it's going to raise or lower the voltage in the bit line. And the sense amplifier senses this perturbation in the voltage and will latch to the correct state. So in the case if we say had a 1 here, it would slightly raise the charge in the bit line. The sense amplifier would sense the perturbation in the voltage, the slight increase in the voltage. It would latch to a 1 and then drive the bit line high again. The reason we want to drive the bit line high is because when we do that, when we start with that charge sharing, we obviously destroy the data that's in the DRAM cell at that point in time. So we need to write back that data, otherwise we obviously don't have the data left after we read it. So the restore operation consists basically of the sense amplifiers pushing the charge back up the bit lines and resetting or restoring the values that were originally in each of the cells on that row. After opening the row, we select a column. Selecting the column basically just consists of picking one of the sense amplifiers, and one of the sense amplifiers in the read operation will then output the data that it has to the bus and down to the memory controller. And in the case of a write operation, that sense amplifier will read the information that's on the bus and take that up and push that into the bit line and to the cell on its column. The delay between when we assert the word line for the first time and when we select the column is called the RAS to CAS delay. And the delay of the CAS delay itself is the delay that it takes between selecting the column and the data being sent out over the bus to our memory controller. In the case of the write delay, that's the delay, CAS write delay is between when we send when we select the column and when we send the data from the memory controller, and it will head up to the sense amplifier. Now in modern DRAM, we, instead of only just reading one column, we read a set of columns, and this will be in the form of a burst. In a burst, we will, in DDR3 and DDR4, send 8 transfers. So we will select 8 consecutive columns to read or write to one at a time, and this will happen immediately after each other. There's also a chopped burst, which will take 4 transfers, and because we're operating at double data rate, the full burst is 4 clocks, and the chopped burst is 2 clocks. Once the burst is finished, then the next operation can happen. So we can either close the cell, so we can close the row, we can continue reading, we can continue another burst, we can we can stack these bursts back to back. But when we're done, we close the row so that we can then select a different row if we need to move on to a different address. To close the row, we quite simply deassert the word line, so we just take off the voltage that we were applying to the word line, and the time between when we start applying the voltage to the word line and when we stop, that's called the TRAS, the row address strobe timing, and that's the full timing between when we start and when we finish. We obviously do need to make sure that the correct data has been read into the cells on the array, the cells in that row before we close the row, because if the sense amplifiers are still restoring the data in the row, for example, then we'd end up with a problem if we close the row before that restoring is finished. After the closing of the row, then we have the pre-charge, which sets the bit lines back to half of the operating voltage, and then we can start with another row. So here we can take a short look at the first divergence between the read and the write operation. In the case of the read operation, we obviously need to have a correct value in the sense amplifier. So we do have to wait until the sense amplifier is stable and it's latched correctly onto the value of the that was in the cell of that column. In the case of the write operation, we don't actually need to worry about this, because we're actually going to change the value in the sense amplifier, or we're going to set the value based on what we're trying to push to the sense amplifier from the bus. So in the read operation, we need to be careful that we wait enough time for the sense amplifier to settle to the correct state before we select our column address, before we select the sense amplifier and start outputting that data to the bus with the CAS with the column address select. And because of this, the CAS in the read cycle, so the normal CAS delay and the RCD read timing, are both generally longer than the RCD write timing and the CAS write timing. And we can take a look at that in these timing diagrams here. We start obviously by asserting a word line here. This is when our RAS timing would start. We go all the way down here, and then we close the RAS obviously before we start the pre-charge. So that's the full RAS timing. Now our CAS write delay here will be shorter than our RAS to CAS write delay will be shorter than our RAS to CAS read delay, and our CAS write latency can be slightly shorter than our CAS read latency because of what we said earlier. Now there's another divergence here, which is the write recovery, because obviously we need to have the sense amplifiers, when they receive data from the bus, correctly set the cells in the row, the respective cells in the row, to the value. So the write recovery time, if we go back to here, say if we're writing to this row, that lets the sense amplifier have enough time to push the correct value back up to the cell in that row. So the write recovery time happens after we finish the data burst, and that's some extra delay that we need to account for before we close the row and deassert the bit line. Because if we deassert the bit line, we'd end up with the same problem we had earlier, that we're closing the bit line before we've written the correct values into the cells on the row. So there's this additional timing here to account for. Now I have some typical timings that we might use when overclocking here. This is for typical BDI overclock at say 36 to 3800, maybe 1.4 to 1.45 volts. We have a RAS to CAS read delay of about 14, a CAS read delay of 14. A data burst would obviously take 2 cycles. Our RCD write would be about 8. CAS write we can have 12 to 14. 12 would be a bit optimistic, I think, but let's put it here as 12. Data burst of 2 followed by a write recovery of 10. So So in theory, our read cycle would actually be shorter here because we'd have, what is this, 22, 32 cycles here. So 32, and then this would be 30 cycles when this read cycle finishes. Now, in actual fact, the RAS delay, so the time between asserting the bit line and asserting the word line and deasserting it, is actually variable, because obviously we need to account for that. We're not just going to transfer chop bursts. We might transfer a long burst. We might actually hold the row open for some time because we might want to come back to it later. So in actual fact, the RAS timing is only a minimum value. It's the shortest time that we can select the row address and assert the word line. If we have a longer data burst, what will happen is the memory controller will essentially by itself, it will increase, it will hold the voltage on the word line and continue to assert it until we can start the pre-charge. But of course, we do need to ensure that the shortest possible value for the RAS timing does allow us to validly restore any of the data in the row we just opened. So in this we can actually see the third divergence is that in the case of a read operation, we don't actually need to have the word line asserted after the restore is complete. So if our restoring the data happens quickly enough, we might not actually need to wait all the time after all the time with the row address open with the word line asserted, because we already have the correct values down here in the sense amplifiers. So we don't actually need to we don't actually need to have the bit line asserted anymore once we have finished with setting the sense amplifiers to the correct value and restoring the values in the cells, because we can just read out of the sense amplifiers without them being connected. Now obviously we can't start the pre-charge, because if we started the pre-charge, then we'd have a problem that we're disturbing the voltage on the bit line, and that disturbance might affect the sense amplifiers. And if we affect the sense amplifiers before we finish reading the data from them, then we might end up with some error there. But there's actually a lot of circuitry between the sense amplifier and the memory controller, and the cast delay is actually not is not just between when we select the column and when the sense amplifier starts outputting to the bus. It's actually until when we've finished, so until when the signal arrives at the memory controller. And because of that, there's actually a lot of propagation delay that we need to account for here. Through 15 centimeters wire at half the speed of light, which would be pretty typical for the propagation speed through a wire, we'd be taking about 1 nanosecond to cover that 15 centimeters. So that would be 2 full clocks at DDR4 4000. And not just that, we need to account for the circuitry as well, because there's a bunch of latches and gates and drivers that need to drive the circuitry out over the memory bus, because that's quite, that's a long piece of wire, so it needs to have a powerful driver to correctly get the value across that bus. And because of this, the pre-charge can actually start not when the burst is finished, like we see in this diagram here, not after the burst is finished, but after the data has actually left the sense amplifiers. So the data might actually be down on its way through the memory bus here, and it's already left the sense amplifiers, but we can actually start the pre-charge already, because it's, as we said, was left the sense amplifiers. So I can actually have a shortened read cycle, and in the case of the shortened read cycle, we account for the time it takes for the data to leave the sense amplifiers and get out safely to some other latch, with the read to pre-charge timing, and that's the timing between when we start the column select, so the same time as the cast delay starts, and then that ends, we can start when that ends, we can start the pre-charge. We actually need to add the two clocks for the data burst, obviously, on top of this, because this would happen from the read to pre-charge would be happening from when the first first column is selected to when the first column is safe and clear of the sense amplifier. So we need to add the 2 seconds for the rest of the columns in that burst to clear the sense amplifier, and then we can start the pre-charge. And because of this, the read cycle can actually be shortened by quite a lot relative to this one. So we might see a read to pre-charge timing of, say, 10, and in that case we'd still have obviously the same RCD read to contend with, so it'd be 14 here, 10 and then the extra 2, but we'd actually be able to start our pre-charge only 26 cycles after we'd first selected our row, after we'd first asserted the word line. So we actually can cut down our RAS timing all the way until we've satisfied the RCD read, the read to pre-charge, and then the 2 cycles for the data burst. And so the shortest possible scenario we can have is that RCD, RTP, and 2, not what's commonly mentioned, which is the RCD, the cast delay, and then the 2 for the data burst. And in some cases we might potentially obviously see that the shortest limiter might be the RCD read, cast, the data burst, and the write recovery, but I haven't actually seen any scenario in practice where a memory die is able to do such a short RCD write and cast write and write recovery that this is shorter than either this long read cycle or this short read cycle. One thing to keep in mind obviously is that, I think as I mentioned before, the RAS, the time between selecting the word line and starting the pre-charge is obviously variable depending on the length of our burst. So if we had a burst that's 4 clocks long, then we'd potentially increase the delay of the RAS. And in the case of the write cycle, we obviously need the RAS to be selected. We need the the word line to be asserted all the way until we finish the write operation, because otherwise we wouldn't correctly end up with the values that we're writing to the cells in the cells. So obviously we can only take advantage of a short RAS timing in the case of a short data burst and in the case where the row is being immediately closed. And because of the fact that in modern processors we are not trying to, we generally want to make use of good bandwidth. We don't want to spend all this time, to spend the RCD read, the cast delay, only to do a data burst that's 2 clock cycles long. We want to try and keep the row open. So in a program, we'll set up its data in a way that it doesn't need to continually open and close rows. And the memory controller will also try to do this, where it will schedule the memory accesses in a way that minimizes how much we have to wait for opening rows and closing rows. So while we can make it shorter, it's not very it shouldn't be something that you see a big performance advantage out of. But in these cases where you do have some short data bursts happening, you should be able to see an advantage by shortening your RAS timing like this. So yeah, that pretty much covers it. So the shortest RAS TRAS timing you should be able to set would be the RCD read, the the read to pre-charge time, and then the 2 cycles extra for the data burst. So that's it for this video. I hope you found it useful. I hope you liked it. It's the first long video on the channel. Comments, of course, down below if you have any comments, suggestions, or anything. Otherwise, if you want to have a longer discussion, easiest place to reach me is probably going to be Max Hardware Numbers public Discord. I should have it linked below, and I'll have my Discord ID linked there as well. So yeah, that's that. I hope you learned something. See you in the next one.